All right, welcome to this explainer. Today, we're diving into the ultimate showdown between human ambition, sheer engineering genius, and the immense, frankly terrifying forces of nature. We are going to explore the top 10 tallest completed buildings in the world. And listen, this isn't just about stacking a bunch of steel and glass. We're talking about pushing the absolute, literal limits of material science and physics.
Because here's the fundamental paradox of megatall construction. How exactly do you build half a mile into the sky without the wind just tearing it right down, or an earthquake snapping it in half? As we climb higher and higher, gravity isn't our only enemy anymore. Up there, wind acts like this massive invisible ocean current that's constantly trying to bend these towers, all while seismic forces threaten to just rip them right out by the roots.
And then, of course, there are the financial stakes. Conquering the sky is easily one of the most expensive human endeavors on the planet. We're talking about singular structures that can cost up to $15 billion to complete. Yeah, billion with a B. So let's jump into this countdown and see exactly where all that money goes and how engineers are actually keeping these modern marvels standing. So let's kick things off with Section 1, Conquering Earthquakes and Wind. Looking at buildings 10 through 6, it is fascinating how uniquely each one of them solves its own environmental threats. At number 10, Beijing's CITIC Tower stands 1,732 feet, or roughly 528 meters tall, right in a highly active seismic zone. To survive that, it uses 112,000 tons of niobium alloyed steel. This basically gives the metal super flexibility without adding crushing weight. Number 9, the Tianjin CTF uses these brilliant soft braces that actually bend with the wind. Number 8, the Guangzhou CTF utilizes smart terracotta on its exterior to manage brutal coastal heat and wind. And skipping to number 6, South Korea's Lotte World Tower, towering at 1,821 feet, uses a massive diagrid crown to disperse the wind, plus these unbonded piles deep underground. Those piles allow its 750,000-ton weight to settle evenly so the foundation doesn't just crack under the pressure. Now, when we compare our next two, we see two wildly different approaches to fighting the wind. First, the Shanghai Tower, the third tallest building in the world at a staggering 2,073 feet, or 632 meters, it uses a totally passive, elegant design, a 120-degree aerodynamic twist. This twist literally confuses the wind, reducing the overall wind load by 24%. And get this, that design choice alone saved $58 million in steel. On the flip side, the fifth tallest, the Ping An Finance Center at 1,966 feet, just uses sheer, absolute mechanical brute force. It relies on twin 500-ton swinging mechanical dampers, basically these massive pendulums up near the roof, that physically counter the sway of the building during typhoons. So you've got elegant aerodynamics versus heavy mechanical brute force, and honestly, both are total engineering triumphs. Moving on to Section 2, America's resilient sky icon. You definitely know this one. This is One World Trade Center in New York City. Its architectural height was designed to be exactly 1,776 feet, or 541.3 meters. That's a direct, permanent tribute to the year of American independence. You see, this wasn't just built to be tall. It was built to be a profound statement of resilience, rising from ground zero to proudly reclaim the Manhattan skyline. And this totally explains why One World Trade Center is arguably the most robust, heavily fortified skyscraper on planet Earth. The base of this building is literally a 187-foot-tall windowless fortress specifically designed to withstand massive blasts. Its central core is made of 14,000 psi high-strength concrete, which was a complete first for New York. The emergency stairs, extra wide and fully pressurized to keep smoke out. All of this unprecedented, literally military-grade engineering pushes its construction costs to a staggering $3.9 billion. It really is a true fortress in the sky.
All right, Section 3, vertical cities and super elevators.
You know, building a tower that reaches the clouds creates an absolute logistical nightmare. These aren't just office buildings, they are vertical cities. Think about it. How do you move tens of thousands of people up and down half a mile of steel and concrete every single day without them spending half their lives waiting in a lobby? Well, you'd build elevators that travel at 45 miles per hour. That's 21 meters every single second. The mega elevators inside the Guangzhou CTF and the Shanghai Tower travel so insanely fast, they actually have to artificially adjust the atmospheric pressure inside the cabin so your eardrums don't burst on your way up to the 100th floor. But here is the truly terrifying part. What happens if an elevator going 45 miles per hour straight up or down needs to stop in an emergency? The physics here are wild.
If traditional brakes clamped down at that speed, the friction would generate heat well over 300 degrees Celsius. That would instantly melt the brake pads and cause a catastrophic fire. So to solve this, engineers had to develop nitrogen-cooled emergency brakes using space-age thermal materials just to safely halt a plummeting capsule. Crazy, right? We are getting down to the wire now. Section 4, the climax, approaching the impossible. Coming in at number 4 is the Mecca Royal Clock Tower in Saudi Arabia, standing 1,972 feet or 601 meters high. This is that $15 billion titan we mentioned at the start of the explainer. To put it in perspective, the clock faces alone are 141 feet wide. But engineers ran into a massive problem here. The building was simply becoming way too heavy for its own foundations. So, their solution? They actually had to abandon concrete entirely halfway up and construct the whole upper clock section out of a 12,000-ton, lightweight, hybrid steel and carbon fiber frame, literally saving the structure from sinking under its own colossal weight.
Leaping right to number 2, we have Merdeka 118 in Malaysia, towering at an unbelievable 2,227 feet or 679 meters. To even reach this height, they had to use cutting-edge C105 basalt concrete, which gives the mega columns unparalleled stiffness. But to truly secure that number 2 spot, it features a massive 527-foot spire. Now, a spire that tall acts exactly like a giant sail in tropical winds, which is incredibly dangerous. So engineers cleverly designed it as a 3D space truss with wind vents built in, allowing those harsh storms to just blow directly through the structure rather than pushing it over.
And finally, number 1, the pinnacle, the Burj Khalifa.
The Burj Khalifa in Dubai, 2,717 feet, 828 meters. That is over half a mile straight up. How did they even do it? Well, they had to invent a completely new structural system called the buttressed core. Step 1. A massive hexagonal concrete core acts as this ultra-rigid spine for the building. Step 2. 3 Y-shaped mechanical wings buttress that core, physically locking the tower in place so it can't twist in the wind. And Step 3, and this is my favorite part, because the soft sand of Dubai couldn't possibly support the 500,000-ton weight of the building, they drove 192 deep friction piles into the ground. These piles don't even sit on solid bedrock. Instead, they use the physical friction of the sand tightly pressing against their sides to hold the entire 500,000-ton structure aloft. It is just absolute pure genius. So, looking at the summary of the top 10, what's truly mind-blowing is the wild variance in cost. I mean, look at the Burj Khalifa and Merdeka 118. Both cost around $1.5 billion. But then you look at One World Trade Center at $3.9 billion because of its military-grade security requirements. And then the Mecca Clock Tower at an astronomical $15 billion because of its massive footprint and those complex hybrid materials. The height really is just half the story here. It's the unique engineering constraints that dictate the true price of scraping the sky. We have seen how humanity has bent steel with niobium to survive earthquakes, elegantly twisted glass to trick the wind, and actually utilized the friction of loose sand to hold up half a mile of solid concrete. We've mastered wind, gravity, and seismic fury. So it leaves us with one final, pretty profound question. As our ambition continues to soar ever higher, what invisible, natural barrier will megastructures be forced to conquer next? Thanks so much for exploring the heights of human engineering with me today in this explainer. Keep looking up.